All right, so we're going to look at molecular shapes. So I have these models, and I'll walk them around so that you can see them better as we get through that. But in these models, I have these different color spheres that are representing atoms, and I have these pieces here that are going to represent covalent bonds. Okay? And so we're going to go through, we're just going to go through these and fill it in, and you'll kind of see what develops as we go through and fill it in. So I want you to fill it in with me, okay? All right, so we're going to start with our first one with, number one, we're going to start with an AX. Oh, I don't know why I did that. We're going to start with AX. It's shifting after I write. I'm not really sure why. All right, so A and X are representing two different atoms, okay? They're representing two atoms. So the 3D picture that we're going to have with A and X, if you just have two atoms bonded, you have A with a line bonded to X. A with a line bonded to X. So let's model that. If I have, let's say the silver that I have here is A, and I'm going to stick a bond in, and I'm going to bond that, let's say the green is X. Okay, so I have two molecules. All right, and I want to look at what is the electron geometry. Now, when you're talking about geometry, you're talking about the shape of things, right? Y'all are in geometry this year, correct? Last year? Okay. So when you're talking about geometry, you're talking about the shape. And so we're looking at the shape of this. How would you describe the shape of this molecule?
A line segment.
A line segment? It's straight, right? So we're going to call that linear. Y'all gonna have to ignore my handwriting because for some reason the board is just, when I write, it shifts it down a little bit. I'm not really sure why. So the molecular geometry, the shape of the whole molecule, is also linear. It's in a straight line. And as we get into bigger molecules, you'll see the difference between the electron geometry and the molecular geometry. All right, bond angles. Do you see any angles here? No. You've got to have three atoms. To have a bond angle, you've got to have three atoms. How many atoms do we have in this one? We have two. So we're not going to have any bond angles in this one. So we're going to write NA there. No bond angles. We have no hybridization. That is an A. It keeps looking like a triangle, but that is an A. All right, polar and nonpolar. If you think back to those words, the meaning is if it's polar, one side of the molecule is charged, or the sides of the molecules are charged. One is positive, one is negative. If it's nonpolar, everything is equal, okay? There's no stronger positive charge on one side and stronger negative charge on the other. Everything is equal. So, polar and nonpolar. If A equals X and if A does not equal X. Now, what that means, A and X are representing two atoms. Are my atoms the same thing here? Are these the same atoms? No, this would because I've got a silver and a green. So this would represent an A not equaling X. If I wanted to represent an A equal to X, I'd put the same sphere on each side to represent A is equal to X, meaning they are the same atom. Okay? So let's go back to A is not equal to X. Do you think that this would be a polar or non-polar? Do you think it'd be shared equally, or electrons being shared equally, or no? No, you got two different atoms. So if A is not equal to X, then it is non-polar. Y'all see how it shifted that? I don't know why I did that. But what about if I change it and I make A equal to X? Do you think that would be polar? Or, I'm sorry. Let me back up. Nobody call me on that. If A does not equal X, they're going to be shared unequally, right? One's going to have a stronger pull than the other. If they're shared unequally, then they are P, polar. If A does not equal X, is polar. My bad on that. I got to going too fast. Got excited about molecules over here. All right, but if I undo that and I make it where A does equal X, then are those going to be shared equally? Yes, because those are the same atom on each side. So yes, they will be shared equally. So that is going to be non-polar. There's no side that has more charge than the other. So that if A is equal to X, that is going to be non-polar. So an example of a non-polar might be an H2. 2 hydrogen atoms bonded together. It could be a Cl2. It could be an F2, like we saw in the activity that we did just before this. An example molecule for the polar one might be HF, hydrofluoric acid, because you've got a hydrogen and you've got a fluorine. Those are two different atoms. Okay? All right, so let's look and let's see what happened in the next one, okay? All right, if we have A, X, y'all, this is not going well with this writing. A, X, 2. Okay, so you have A as a central atom, and then we have X is another atom, but we have two of those. So what's going to go in the middle, A or X? A. Okay, because we got one A, we've got two X's, so we're going to put A in the middle. So I'm going to get two of my bonds here. And I've got two X's, so I'm going to use green to represent the X's again. So this is what we would look like as an AX2. Okay? So I've got one central atom, the silver one. The bonds here and the greens are going to be the X's. So as far as how we would draw that, that would be A in the middle. Can y'all tell what I'm trying to draw with this? Okay. All right, it should be an A with two lines out and then the X's on the sides. So you've got a single bond on each side of A with the X on the side. What kind of geometry would we call that? What kind of shape? Linear again. And it's going to be the same thing for the molecular geometry. It's going to be linear. So we got 3 atoms now, so we can say that we have a bond angle. What is this angle gonna be? If it's linear, what is my angle?
180.
180, okay? So my bond angle is 180 degrees. 180 degrees. Now, when we're looking at hybridization, we're looking at our s orbitals and our p orbitals. And in this, you are going to have a hybridization of s and p. So our hybridization is going to be sp. Do you think that this is going to be polar, where it's shared unequally, or do you think it's going to be non-polar, where everything's equal?
No, it's gonna be non-polar.
It's non-polar. Okay, everything's equal. Everything's equal, so it's non-polar. It's non-polar. So an example of this might be carbon dioxide. Whew, gracious. Let's try that again. Or another example of this might be like a BeCl2. Anything we have one central atom and 2 here, that's going to be linear. Now, let's change this up a little bit, and let's say that we have, we're gonna call this next one here AXE, and the E is going to stand for electrons. The E is going to stand for electrons. So let's say that we have an A and an E, or an A and an X, I'm sorry. But we also have some other valence electrons. You know, when we were drawing those bonds, not all the electrons bonded, right? Not all of them shared with something else. There were some electrons that were just left. Yes, Jason? AXE. Yes, AXE. And so we're going to put this little balloon-looking shape here. All right, and that's going to represent electrons for us. Okay, that's going to represent spare electrons that are not sharing with anything else. Okay? What shape are my atoms in still? Linear. They're still linear. Okay? I've got the electrons here, but my bond and my atoms are still in the linear shape. Alright, so they're still linear. The overall geometry, the molecular geometry is still linear. It's still on a line. So I'm going to write linear here. Alright, for my shape, right, this 3D picture, I'll skip that. You're just going to have X, A, and then you just got a pair of electrons. I'm going to put 2 dots there to represent a pair of electrons. Yes. X line, A line, and it's supposed to be 2 dots, not 3. It's supposed to be 2. This board and I are not getting along today. All right, so do I have a bond angle? How many atoms did I have to say I have to have a bond angle? To have 3. I only have 2 atoms because this is electrons coming off to the side here. So I only have 2 atoms. So there is no bond angle. All right, so let's look at if I am polar or nonpolar. All right, so if A is equal to X, Let's see if I've got one where I can do that. If A is equal to X, let's see. I don't have one where I can stick the electrons in the side there. But if I have the same thing, is that going to be polar or non-polar? If I have the same on each side.
Non-polar.
That's non-polar. They're going to share equally there. So if they're the same, if A is equal to X, that's going to make it non-polar. You write it higher. We'll shift that down. I don't know what the board is doing. But A is equal to X. That is non-polar. But if A is not equal to X, is that polar or non-polar? Polar. They're not going to share equally. So we're going to have some opposite sides. Think North Pole, South Pole. Opposite sides. We're going to have some sides that are different there. So if A is not equal to X, that's going to be polar. So an example might be N2. Like when we put those two nitrogen together in that activity before, we had some electrons left over. An example of the polar one might be carbon monoxide. CO, carbon monoxide. All right, let me scroll up here. All right, let's look at the third set here. Let's look at if we had a central atom A, and we had X3. That's an X. It's supposed to be. All right, AX3. Let's say we had AX3. So we got 3 of one atom and 1 of the A. All right, so this black molecule or atom, this is going to be our A, okay? And then we're going to get, let's just get the greens again. We'll go with the greens. And let's get some bonds here. So when you place the atoms around, you've got 3 atoms, and you're going to place them around this one atom. How do you think they're going to be placed? Okay. Let's see. Kind of like a peace sign, right? Let's see. I'm going to make sure I'm doing the right ones. Let's see. Here we go. We're going to use the beige one, not the black one. The wrong central atom there. Okay, so the A is going to be represented by the beige. The X is going to be represented by the green. So we have our little peace sign looking molecule. That's not linear, you're right. This is not linear. Okay, so this is what we're dealing with when we have one central atom and we have 3 around it. Okay, so this is going to be AX3. What shape does it remind you of?
A triangle.
A triangle, okay? We're gonna use, because there's three, we're using that prefix tri. We're gonna call this, and because it's on one plane, we're gonna call this trigonal planar, P-L-A-N-A-R. Trigonal planar. That's gonna be the shape of this. And so if we draw it, you're gonna have your A in the middle here. Oh, this is gonna be hard right here. A. And then you have X. Let me draw that in the notebook here. So your shape there is gonna be A, X, X, X. There you are looking at your shape, okay? So what do you think the degrees is, the bond angles? Do we have, well, first of all, do we have bond angles? Yes, because we have at least 3 atoms. So we have bond angles. Do you think they're equal? The bond angle here, 1, 2, 3, that angle, this angle, and this angle. Do you think they're equal?
Yes.
Yes, they are equal because they're evenly spaced, and it's the same atoms here. So what do you think the bond angle is? 360 divided by 3 would be 120. So your bond angle, you've got 120 degrees here, you've got 120 degrees here, and you've got 120 degrees here. So if I go back to my paper, I'm looking at 120 degrees. This right here, this box right here, this geometry is also going to be trigonal planar. That's going to be trigonal planar as well, with 120 degrees. We look at our hybridization, that's going to be sp2. All right, do you think that this is going to be polar or non-polar?
Non-polar.
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 It's non-polar because everything's going to share equally because we have the same 3 atoms on the outside. They're spaced evenly. So this is all going to be non-polar. There's not going to be one side that's more positive and one side that's more negative. It's all going to be non-polar. All right, and so when we look at an example, a good example might be BF3. So if you see an example written like that, that's what we're going to have. Okay? Well, let's look at something different, though. Let's look and see, what if we have AX2E? AX2E. Meaning we've got 2 of the X atoms connected to the A, but we've also got some spare electrons left off that didn't have to bond with anything or share with anybody. Okay? So let's take off one of the atoms, and we're going to add our this little part here that's going to represent just electrons. Okay? All right, so we've got a central atom. Our greens are our X2, and we've got the E right here on top. okay? We're still gonna be the trigonal planar. We're still gonna have a shape of, let me go back to here for the shape. Our shape, you're still gonna have an A, you're gonna have an X and an X, but up here you're just gonna have 2 electrons, okay? Now, when we get to this shape, it is yes, it's a trigonal planar because you've got, that is the electron geometry, okay? How the electrons are moving and how they're positioned, it is trigonal planar. But when we look at the molecular geometry of the molecule, our atoms are here, here, and here. Okay, the 2 bottom and the 1 central, that is our atoms in this. So that's what we're looking at for the molecular geometry. And so for that molecular geometry, how would you describe that? I can flip it even. Ignoring the electrons, you would describe it as a what? A V? How else could you describe that? There's 2 things you can call that. You can call that V-shaped. Real technical there. Or you can call it, here's another really technical word. You can call it V-shaped or bent. Because it's not in a straight line, right? It's like it's bent. Do you think we're going to have equal bond angles here? No, because the electrons here are not the same as these 2 atoms off of here. Before, we had the same thing coming off this end. But they're not the same. So we don't really know the exact, but we're going to say that it is less than 120 degrees. It is less than 120. So do you think that this is polar or non-polar?
I forget what's what.
Okay. So is everything going to be shared equally, you think? No, so it's going to be polar because there's going to be a positive and negative. So that's going to be polar. An example of this one would be a nitrite molecule, which has a -1 overall charge. That's one of your polyatomic ions. But that would be an example of this one. All right, let's do the next one with 3 bonds. You're going to have an A, X, we're going to call that E2, AXE2. AXE2, meaning on 2 sides now, instead of bonds and atoms, we're going to have electrons. So we're going to have AXE2. And that's still a trigonal planar shape. To draw the shape in that little box, all you're going to do is you're going to take one of these and put electrons there.
I don't know, this is scary.
I think that was the drink closet beside the room.
Still be saying this to women.
Now, when we're looking at the electron geometry, the shape involving all the electrons, that's still trigonal planar. You still see that triangle shape. Okay? But our molecular geometry, when we're just looking at the atoms, how many atoms do we have in this molecule? We have 2 actual atoms here, okay? We've got the A and E. What is that shape? What is that molecular shape of just the atoms? Linear, because it's a line. Okay, so we're going to go back to this, and we're going to put linear here. So the electron geometry is still trigonal planar because you're still seeing that triangle, but the molecular of just the atoms is linear. All right, do we have a bond angle? No, because we have to have 3 atoms to have a bond angle. How many atoms do we have?
2.
We have 2. All right, so there is no bond angle. All right, so if A is equal to X and if A is not equal to X, meaning if they're the same atom or if they're different. If they're the same atom, are they going to be polar or nonpolar? Nonpolar. And if they're different atoms, they're going to be polar. Look at y'all. And so an example we might have of the nonpolar is O2, oxygen, what you breathe in. A polar one might be SO, sulfur monoxide. All right, let's go to the next set. And we'll just go into the bell rings and we'll pick up, let's see y'all again Monday. We'll pick up Monday. Jacob. Do what? It's not. We'll talk right after class. All right. So let's look at our numbers here in case you haven't realized it's the number of X's and E's we have on the central atom. So let's look at the 4. Let's say that we have AX4. Okay, so we're going to go back to the marker here. AX4. AX4. So let's get an idea of what shape we're going to have here. I think we're going to go with the silver one. No, this is where we use the black one as the central atom. Because our goal when we can do this, we want to space them as evenly as we can. Let me get our X's. All right, so here is our AX4. And if you look, no matter which way you turn it, they're all spaced evenly, correct? It doesn't matter which way I turn it, it's the same shape and the same spacing, no matter which way it turns. Okay? We've got the same spacing. which way we go with it. Okay, so let's look at what the 3D picture would look like. Let me go back to our notebook to draw that. So I've got my central atom A, and I've got my X that comes up, and I'm going to draw an X that goes down, and then just to make it look kind of 3D, if you look at a drawn picture, it kind of does a wedge here. If you see drawn diagrams, that's what that will look like. Now, what is the prefix that we used for 4? Tetra. The shape of this, if I go back to my chart, the shape of this is called a tetrahedral. Let me spell that for you because I know it's hard to read. Actually, I spelled that wrong. Hold on. Let me see if I can fit it in there. Okay, that's supposed to be a tetrahedral, T-E-T-R-A-H-E-D-R-A-L, tetrahedral. Tetrahedral. Or you can call it a tetrahedron. Either one. Tetrahedral or tetrahedron. Tetra, H-E-D-R-O-N. Now your bond angle. Do we have bond angles?
Yes.
Yes, because we have more than 3 atoms. Anybody want to guess what your bond angle would be?
90.
95.
120 was when we had 3.
So
Would it be 90?
360.
No, it's gonna be 90.
I said that.
What is the bond angle? What is the bond angle?
And 360, I thought 4 is 90.
So
Okay, so it's not going to be quite 90 because if you look at this, is this a 90-degree angle? It's a little bit over 90 because 90, this would be straight across, and it's not. It's going down. It's going to be.
Greater than
93.
93.
Here we go, guys. 109.5. 109.5. Because it's not 4 in a straight circle around. You got 1 up and you got 3 down, so they're repelling each other equally. It's a little more than 90. Your molecular geometry here, it is the same as this. This molecular, you should write in tetrahedral or tetrahedron. Okay, the molecular is the same right now as the electron geometry. The molecular is the same. Your hybridization is going to be an sp3. Do you think this is polar or nonpolar?
Non-polar.
This one is nonpolar. This one is nonpolar. An example molecule might be a methane molecule, CH4. CH4. And we're going to stop right there for that. I want to see your paper before you put it up.